Aloha and welcome. My name is Maddox Oye and I'm a senior at St. Andrew's Schools, the Prairie. Our school is a proud partner of the Waikiki Aquarium Distinguished Lecture Series and is honored to support the mission of bringing the latest ocean science research to our campus community and the public at large. This is the first in-person lecture since March of 2020 due to the COVID pandemic, and we are so happy to welcome you back to Tiny Theater. I am honored to be here tonight because I am passionate about this topic of sustainability and environmental science. During my time as a Prairie student, I have had opportunities to pursue this passion through classes, clubs, and through my senior internship, which have allowed me to understand sustainability and has helped me decide my future in this work. My passion for sustainability started in sophomore year with AP Environmental Science, which gave me exposure to the different anthropogenic impacts and the baseline knowledge of this field. APES propelled my interest and from there inspired me to take multiple environmental-focused high school and college classes, join our school's PAC club, and pursue our school's distinction in global leadership. Here I find myself in my last semester of my senior year, interning under renowned climate scientist Dr. Chip Fletcher. As a passionate student who plans to pursue a career in this field, it is exciting to introduce a guest speaker who I find inspiring and who is working to create positive change in his scholarly and career endeavors. Our speaker tonight has also embarked upon a future focused on sustainability, that is of coral reefs. Zackery Rago grew up in Colorado, but spent summers on the Big Island getting to know its amazing ocean life. After graduating from the University of Colorado with a bachelor's degree in evolutionary biology and ecology, Rago worked for a marine imaging technology company. In 2017, he was featured in the Netflix documentary Chasing Coral, where he helped film the first ever time-lapse of a coral bleaching event. After the film was released, he worked with science communications and youth outreach programs. He is currently pursuing a PhD in marine biology at the Hawaii Institute of Marine Biology. Tonight, he will tell us about coral reef halos and the role that fear can play in the conservation of coral reefs. Mahalo for coming to our campus tonight, and please welcome Zackery Rago.
Well, thank you everybody first and foremost for coming tonight. I'm really excited to give this talk. It actually comes at a really good time for me because I'm taking my comprehensive exams in like 3 weeks. So it's also a really good practice run for me. But first, I'd just like to thank the Friends of Waikiki Aquarium, the aquarium in general, St. Andrew's School for hosting this. I'm really honored to be here. I'm honored to share this research. I think that's really interesting. But yeah, at that, we're going to be talking about fear in fish, kind of an interesting topic, and more importantly, what can fear do for conservation, which I think is this very abstract concept. But in order to go through that, I'm going to kind of actually reiterate what our intro talked about and kind of give you a background on my own life, because I think that my experiences growing up have largely driven how I got to the current position that I'm in, and have largely driven the questions that I'm asking currently with that research. So to start, as was mentioned, I grew up in Colorado, so before I was swimming around in the tropical turquoise waters here in Hawaii, I was actually spending more time in turquoise waters that were just a touch colder. I bring Colorado up in particular because that ecosystem is dramatically different than a coral reef. And I put this picture in here because we're going to circle back to this exact ecosystem later on in this talk, but this is the type of system that I grew up around. Much larger apex predators, much larger herbivores, but it's important to the concepts that I'm going to talk about in this lecture. That being said, I grew up in Colorado. I think it's an incredibly important part of my life because the natural world in Colorado is incredible. We have the Rocky Mountains. It's a lot of open space. We have a lot of natural open environments. And I grew up spending most of my time down at my local ponds, catching snakes, catching lizards. I thought that I was going to grow up to be the next Steve Irwin. But as was mentioned, my dad and my mom are both educators, and I spent my summers out in the Kona Coast, actually. My dad teaches a program basically teaching high school kids about marine biology out in Waimea. And so I grew up spending a lot of my summers looking into the tide pools on the Kona Coast, and it ultimately drove me to kind of lose that interest in herpetology and reptiles and drive me into the mysteries that include the oceans. That experience, obviously, I got to go through that program with my dad, got scuba certified out in Kona, just continued to fall in love with the ocean. That opened some more doors for me. I did a bunch of work in Belize, working on coral reef ecology when I was a senior in high school. And I just continued to try and drive pathways into being able to find a career path into the marine world. As you can imagine, that's quite difficult to accomplish in Colorado, so I kind of circumvented that by getting heavily involved with the aquarium industry. I know that's a funny topic to bring up here in Hawaii, but it's the reason why I'm here. It drove my interest, and it made me, I think, a better scientist because of it. We used to grow coral. Basically, I worked for one of the best coral growing operations west of the Mississippi, located in Colorado, called Reef. We had massive grow-op tables. I learned so much about the diversity and taxonomy of coral in that process. And I was obviously still an incredibly passionate reefer myself. This is my home aquarium that I had to leave behind when I came out here. But generally speaking, I think that the aquarium industry drove a lot of my love for the ocean, and it enabled me kind of this pathway from Colorado to be able to continue working in that space. Now, I had to go to college, obviously, and I stuck in Colorado. Again, difficult to find the space to work in the marine world, being in Colorado. And I actually mostly worked on plants, ironically enough. Again, circling back, this is going to become slightly important as we get into the nitty-gritty of the research that I currently do. Mostly worked on things like adaptive radiation, on things like ferns, orchids, but I have a soft spot, I think, for the things that don't move. So many people love megafauna, the whales, the sharks. Well, the plants and the corals are what got me off growing up, apparently. Once I was out of college, or kind of at the end of my collegiate career, I got involved with a company that was building underwater technological systems, particularly on imaging. So these are really cool cameras. This is essentially on the inside just your average security camera. It's covered in a giant glass dome, and this ring here at the bottom is a set of magnetic arms. There's basically a partner set of magnets on the interior of this, and a little rotor that pulls that magnetic arm, and this arm right here essentially acts as a windshield wiper, so we got this technology patented. As you can imagine, many of you, because we're in Hawaii, know that the limiting factor in our oceans are essentially a competition for space. When you put clean glass underwater, it takes like 12 hours for things like calcification to start taking place. That glass gets very dirty very quickly, and this technology allowed us to circumvent that so that we can take long-term imagery underwater. It's a really difficult process, but it's something that we developed to a point that now we have these cameras all over the world. This is one of our first systems that we put in probably back in 2012, 2011 in the Cayman Islands. And this is actually a camera that we put in at my current job. Out at HMB, it was donated to Ruth Gates back in 2018. And this camera is actually sitting on my desk at work right now, and we're trying to figure out something to do with it. That being said, I want to show you just a little bit of why this technology is cool. I think it's twofold. First and foremost, it allows for remote monitoring in live time. So this is actually run by John Burns. He's out at the University of Hilo, did his PhD at the Hawaii Institute of Marine Biology as well. This is a really cool little highlight video where we're seeing a bunch of big aluas back here. Please take note of them. They're also going to become more important as this talk goes on. We also see some amilus back here. So we're seeing this interface of predator and herbivore interactions even happening in this video. But the main takeaway is these cameras were cool because they allow people that maybe don't get the opportunity to spend time underwater to get a little bit of a glimpse into what it's like to spend time in a marine environment, to see coral reefs, to essentially be able to have a little bit of participation in these worlds that are only available to those of us that either snorkel regularly, are surfers, are scuba certified, and that's less than 1% of the population. People don't have close, tight-knit relationships with coral reefs in the way that they do in many other ecosystems. And this technology, I thought, was just an incredible tool to not only get people more involved, but also give scientists a little bit more freedom to monitor places in real time. Working underwater is incredibly challenging, so if you can open the door to have live monitoring, this is a big game changer for us. And so I've worked in that space for a really long time. I did it for about a decade, putting cameras all over the world. But really what changed it for me was when this guy walked into our office. This guy's name is Jeff Orlowski, and many of you are probably like, I came to a talk about coral reefs. Why is there a picture of a dude on a glacier? He made a film called Chasing Ice back in 2011, a film that I was actually quite fond of, had seen in my undergrad. And basically his goal with that film was to document how climate change and anthropogenic stressors were influencing our polar regions, and in particular, how they were influencing the disappearance of glaciers. He did that through time-lapse photography. So he set up trap cams on the side of mountains in Greenland, Alaska, Iceland, and basically documented how things were changing. I think that this technology is really interesting because we live in a time and space as people where we're getting our information in 30-second snippets from our phone, whether it's Instagram, social media, what have you. And so much of what's happening in terms of life on Earth happens in the slow lane, and a lot of that is unable for the human mind to grasp. We aren't good at taking that type of information and understanding that things don't necessarily happen at the pace of our human lives. When you can manipulate time with things like time-lapse photography, you actually open the door for that information to become digestible to people. You're not throwing graphs at people, and you're allowing them to see what's happening in a time frame that's actually able for the human mind to take it in and to digest it and to make sense of it. But he wasn't reaching out to us because he wanted to keep working in the Arctic. He was reaching out to us because quintessential coral reef ecosystems like this, built up of incredible colors, incredible structures that provide this habitat for essentially a third of the organisms in the marine environment, are changing rapidly. And what he wanted to do was document a reef system that looks like this, transitioning into a reef system that looks like this. Now, the purpose of this talk is not to talk about bleaching as I usually would do, but I will briefly describe what that process looks like. These corals that you see before are actually not colorful themselves. They have a symbiotic algae that lives within their tissue. That symbiotic algae essentially produces food for the coral through photosynthesis. As waters get too warm on coral reefs, that symbiotic algae, rather than producing food, starts to produce really nasty chemicals called reactive oxygen species. The coral then recognizes, I have something inside my body that is harming me. I need to think about how to save myself. And so it removes that and leaves behind the stark white skeleton and a small layer of tissue behind. These corals aren't dead, but they're in serious trouble if that temperature does not decrease, and we call these events bleaching. So the goal of the project was to document this transition from beautiful, colorful, quintessential coral reef to a bleaching event. However, we didn't necessarily realize that in 2014 through 2017 we would be on the forefront of what would ultimately become the largest coral bleaching event that's hit the entire globe in history. And we didn't realize that ultimately we would be going beyond bleaching and documenting these quintessential beautiful reefs falling apart and essentially becoming these rubble fields. So I worked on that from 2014 to 2017. It essentially changed my life. I was a 23-year-old kid that wasn't even supposed to be in the film. They ended up telling my story as part of the film. And this talk isn't about chasing coral, but I feel obligated to at least show some of the time-lapse footage because it's a core component of my life. It's a core component of what got me here. And I think that it never hurts to at least share the story of the current situation that coral reefs are faced with. The bleaching events that happened around the world from 2014 to 2017 were severe in nature. We lost about 50% of the corals on the Great Barrier Reef in a 2-year span. Essentially, it was unprecedented, and these things are continuing to happen at a rapid pace. And this is really just to prove that we need to come up with novel and innovative conservation strategies, not only for the corals, but for marine ecosystems as a whole, because marine systems are difficult to work in. We know less about them than their terrestrial counterparts. And in doing things like this and sharing the good word, we're able to kind of promote and push forward work and research that's trying to identify cool and novel ways to think about how we move forward and make good decisions for conservation. Now, this project made a huge dent on that front, I think. We were on the front cover of Time magazine, the front cover of New York Times, and we even saw Nature magazine, one of the largest publishing for scientific articles in the world, having corals that were bleached on the front cover. Now, after the film came out, I worked extensively in activism, education, and outreach. I led essentially a charge. We hired a huge team to both work on the political front as well as on the educational front to educate folks about what's going on in the coral reefs, but more to talk about climate change and what we can do on the political space in order to combat these issues. Because at the end of the day, all of the research we do in terms of protection and conservation is only meaningful if we have the top-down, top-down's funny because that's going to come up again, unless we have the top-down control that's happening from governmental standpoint. Unless we have the government actually stepping up and holding their end of the bargain, anything that we do on the scientific front is ultimately moot. But as much as I love activism, outreach, and education, and it's still a core component of what I do today, I wouldn't be standing in front of you if I believed otherwise, I was kind of bored. I didn't want to be doing this anymore. As cool as it is to show a film in front of Congress or in front of the United Nations, I really wanted stimulus in my life, and I probably would have came back to grad school pretty quickly if it weren't for my little detour with the filmmaking. And I kind of kept an eye peeled on different opportunities that could come about for me in terms of graduate school that felt like they fit the bill for where I currently was in my life and that supported the experiences that I had had to date. And I actually found a tweet that came across from Dr. Elizabeth Maiden here. And her lab is really interesting because she kind of works at this interface of large-scale human impacts, emerging technologies, and this concept of landscapes of risk. And so as I was reading this tweet and this kind of job proposal, I ended up looking through and I was like, well, hey, large-scale human impacts, I've been working on that for a while. I just documented the first coral bleaching event through time-lapse. Emerging technologies, I've got that under my belt. I designed these cameras, we have patents. I'm one of the world-leading experts on how to use this particular camera system that only works underwater. And conservation solutions, something that I'm obviously passionate about. I love coral reefs. I think anybody that gets involved with science has an inherent love for what they are interested in. But this last one, I was like, I don't know much about that, but it's a cool term, and I think, let's reach out and see if this is a good fit for me. So I did that, and I got the job, and it turns out that Liz is kind of the godfather or godmother of coral reef halos, which is really what the main point of this talk is going to be today. These coral halos are fascinating landscape patterns. So to just briefly walk you through what you're looking at in this image, the structures that you're seeing here that are kind of greener in color are all reefs. So here's probably the best example where we have small patch reefs, and we have these lighter colored bands surrounding them. That's actually a band of sand directly adjacent to the central reef structure. And as we get farther away, we get darker again. And that's actually either seagrass or macroalgal beds. And so this pattern exists ubiquitously across the planet. This is taken from the northern Red Sea. This is another example that maybe isn't as clear, but again, you're seeing these distinct patterns where you have reef structure and sand surrounding them. This is located, I think, in a small atoll in Southeast Asia. And this is another example where, again, we have the central reef structure, a nice band around it, followed by macroalgal or seagrass beds. This is in the Florida Keys. And what's cool about them is we actually have known about them for quite a while. The first notion that was written about them was by Randall, obviously a very famous and also worked here in Hawaii very extensively. In 1965, saw these in the Virgin Islands along with Ogden just a handful of years later, though they both attributed them to different factors, which I want to talk about briefly because I think going through the history is quite important. So Randall first saw these, and I think it's just so cool that we actually have aerial imagery of this even back then. And if you look at this reef down here, you can actually still see this band of sand directly adjacent to the reef. And then you get into that algal meadow. This is another image from the Bahamas. Again, we have reef structure, a big band of sand, and then algae on the outside. What he thinks was happening was that surgeonfish and parrotfish were using this structure, and they only live on this structure, and they're going outside of it to feed, and they're creating these perfect patterns around them. So in order to test this, very clever back in the 60s, he actually set up basically an artificial reef. And it's just cinder blocks, it's very rudimentary, but in this image in 1960, when he first set it up, you can see that he just placed these out inside of a big algal field. This is all seagrass. And just 8 months later, you can see that all of that algae was removed. Now, again, his concept was, well, obviously big herbivorous fish have to be causing this pattern. What else could it possibly be? However, the interesting thing with this particular study is when he would go back and survey these, he never actually really saw these big herbivorous fish on the structure when he was surveying. So it makes intuitive sense that this is what's happening, but we still didn't really have good data that that was the case. On the other hand, John Ogden, just a couple years later, was saying, well, maybe it's not fish, maybe it's actually sea urchins. And he actually ran some experiments that provided a little bit more insight. So this line here is actually looking at urchin density, and this is distance away from reef here on the horizontal axis. And what we see is that as you get farther away from the reef, the urchin density plummets. And as you get farther away from the reef, this other line is the height of the seagrass. And so we see this very direct link that as the urchin density away from the reef is decreasing, the algal length, or the amount of algae in that environment, is also going to increase with it. So it's a perfect pattern that makes, again, a lot of intuitive sense. But personally, I think that sea urchins, it's not necessarily the best argument in my opinion. However, I did like this picture of an urchin that's obviously overgrazing, kind of created a perfect little halo around himself. However, not everybody agreed on this mechanism that herbivory was the core reason that this was happening. This is another hypothesis that came up when we talk about coral halos, is that hydrodynamics could be running this. When you put a structure in water, you have wave energy coming in one direction. And what this graph shows is that on this A face, basically he did the same thing. Let's imagine that my little coral diagram is actually a perfect square. On this A face, we don't have that much sand building up around it, as well as on D. But on B and C, we had a huge amount of sand expansion. And so what he found was that this pattern should look something like this, where on one side, on the essentially the windward or the leeward side of that wave action direction, we should have an expansion of sand. But that's not what we see with halos. With halos, we tend to see this perfect circle all the way around it. The radius doesn't change. It's uniform all the way around the reef. So I don't think this is what's happening either. But what's funny is, even today, 50 years later, we still don't really agree. This is just from a couple years ago. I'm not going to get into the nitty-gritty of what's being shown on this graph. But basically, people are trying to argue, we are oversimplified these processes. Everybody wants to believe that it's just herbivory or that it's just hydrodynamics that are driving these patterns, but indeed it's probably a big assemblage of all of these different things happening all at once, and that what we really need to do is start to narrow in and isolate these different factors and see how much intensity each one is playing in order to drive the pattern. However, we do know a lot more than we did long ago. So my boss, Elizabeth Maiden, has run a ton of different studies to try and start unraveling some of those mechanisms. One of which was really cool, where she looked at species interactions. She basically found a reef, outplanted algae at a bunch of different distances away from it, and then took a bunch of videos looking at what type of herbivores were going out and what type of bioturbators, things like a goatfish here in Hawaii that stir up the sand bed, as well as all the different predators, and measuring where are everybody spending time if we look away from the structural protection of the reef. And what she found is that obviously predation risk for these small herbivores increases the farther away you go, and that if you can kind of see here, these herbivores and bioturbators really will only spend time within that barren sand zone. So again, we have some evidence that herbivory is driving that pattern formation. Now, I want to give one more cool example. This is very messy data, but I throw it up here because the real important takeaway here is that density is an important thing for us to think about. The more herbivores that you have on a reef, the larger or smaller that halo might be. So let's just briefly talk about these possible mechanisms that we've just ran through quite quickly. On the abiotic side of things, we have hydrodynamics, we have things like nutrient loading, we have temperature, which always plays a significant role, and we even have things like sedimentation. On the biotic side, we know that bioturbation now plays a role from the work from Elizabeth, and we also know that herbivory is obviously playing a role. We just don't know to what extent that actually is going to be driving it. But like I said before, the big thing and the reason why I got involved with this and what my research is trying to do is we need to stop thinking about things in hypotheticals or in terms of all of these things put together, and we need to start isolating each and every one of these to understand how they play a role in the formation of these patterns. For me, I want to look at herbivory. But in order to think about herbivory, I need to give you guys a little bit of background on how we think about food chains, how these species relationships function, and why fear becomes important. So to do that, I want to talk about trophic cascades and top-down control. The best example, and one of the firsts that we have in the scientific literature, is a system that includes otters, super cute, urchins are back again, and kelp forests. Now, when we think about food webs, this is a very rudimentary way of thinking it. We've got otters eat urchins eat kelp. It's that simple. But in science, we can think about these in a couple different ways. We can think about them in terms of trophic levels. So we can put the otters into kind of a large compartment called predators. We can put our urchins into a large compartment called herbivores. And we can put our kelp into primary producers or just producers. We can even expand that to then become functional food webs, where your predators tend to be less abundant, kind of your classic triangle or pyramid, food pyramid. You have that predator having increased control over the herbivores because they like to eat them. So these arrows their thickness represents kind of the interaction strength that's going on between those two species. You have a very strong interaction happening between the otters controlling the number of herbivores occurring on an ecosystem. And these herbivores then can graze, but not overgraze on the kelp. So this system's stable as it stands right now. However, in the 1970s and really through today, we saw a massive shift in these systems, particularly up in the Aleutian Islands in Alaska, Adak Island and Amchatka. And basically what happened, if you look on this graph, we have after decline here in the striped bars, and in our open bars we have before decline. So our urchin biomass before the decline of otters is quite low and controlled, but afterwards it increases in a huge way on both of these systems. Now we look at grazing intensity underneath. This is kind of related to this strength of this arrow. After the decline of otters, we have a massive increase in the amount of grazing intensity that these urchins are placing on kelp. And the kelp density, because of this, now declines in a huge, huge way. So what does this look like within our pyramid? Well, it looks something like this. We've removed all of our otters. This top-down control that we had before now doesn't exist. And we have no more control over the population of our urchins, and so they explode, they overgraze. These arrows are now bigger because this intensity of this relationship is increased dramatically, and we get left behind with a barren ecosystem that lacks kelp completely. So we call this an urchin barren, but this is the first example of kind of a trickling effect through a food web as you start to mess with the top. You start messing with apex predators, and it has a rippling effect or a cascading effect all the way down to your primary producers. So to reiterate, the removal of a top predator can cause a cascading effect that ripples through a food chain, and in simple chains like this, can have a dramatic effect on the ecosystem, going from very stable, having normal abundances of all three species within the chain, to essentially just limiting it to an urchin barren where you've removed the predator, and because the urchins are no longer controlled from top-down forcing, you have removed the primary producer as well. But this isn't the only example of trophic cascades, and where it gets really interesting and circles back to me growing up in Colorado is the classic example that most of us probably learned in our basic biology class in Colorado, or for me in Colorado, is the interaction of wolves, elk, and aspens in Yellowstone National Park. What's interesting here is this is the opposite situation. Again, we can bundle into predators, herbivores, and producers, but we had already removed this apex predator from this system long, long ago. And so this system already looked like a huge population of elk that were basically controlling the entire producer community of aspens within the park at Yellowstone. What's really cool about this example and why it's so infamous is the wolf reintroduction in 1995. This created this basically artificial, gigantic laboratory for food web scientists and ecologists to be able to look at how these systematic changes influence an environment when you add in or remove predators. And as you can imagine, what happened immediately was the wolves decreased the numbers of the elk population, and you started to get the regeneration of aspen in a lot of these places. Simple enough, that's exactly what we saw given it's the opposite situation as our sea otters example, this is a great way to visualize. This is the same picture in 1996 as the wolves were being reintroduced, a relatively overgrazed riparian system, and then just 7 years later, we can see the vegetation has increased quite a lot. And I want you to note that this particular image is quite open in nature. There's not a whole lot of trees or anything, but that's going to become important here in a moment. So wild population shifted in Yellowstone in a similar way to that of the kelp forest in terms of numerical changes. The wolves were introduced, they decreased the abundance of elk and therefore increased the abundance of aspen. There was something else that was really interesting going on at Yellowstone, and that was that, excuse me, although the cascade was occurring in a way that was still looking at a numbers game, what was really occurring, and what's even more interesting, is that we changed the behavior of the elk. So although elk behavior shifted dramatically, they were now avoiding areas that they perceived as high risk in the presence of wolves. And this is just a really cool graph where here you're looking at predicted kill occurrence within Yellowstone, and predicted kill occurrence is just where we think wolves are most likely to kill an elk. This is the actual kill density that we see. We use basically collared tags on wolves and elk to be able to understand what's happening here. This is a measure of openness of the landscape. So going back to this, an open area like this that used to be grazed might be perceived as risky now by the elk, and they may avoid areas like that because of higher risk. And this is the wolf density. And using just these three things, we can produce a map that looks at the predicted kill occurrence. To reiterate here, numerical cascades and behavioral cascades can co-occur. They can occur on their own. But the important thing is to note is that the exact same outcome can happen in both situations. So lethal effects basically just mean it's a numbers game. We have reintroduced otters, for instance, that depletes this level of the food chain and increases this level. But on the opposite end, we have risk effects, which is what I studied. And that is that just the simple reintroduction of the wolves being there doesn't necessarily mean that you're decreasing the population, but it controls that population's behavior to a point that you can increase this level. So what's cool about this is that what we've done is we've bridged the gap between basically trophic ecology or food chain ecology, and we've now placed it over a landscape. So it's not as simple as saying, okay, well you have X number of otters, so therefore all of the urchins are going to be eaten. It's where you're spending time as a consumer that drives the patterns that we see in an ecosystem. So we started to look beyond these lethal interactions, this numbers game, and we started to think about non-consumptive or risk effects. And risk is a perception. People don't like when I use the word fear, but I think that it's a really good term to use because it's what makes sense for us as people. But fear drives things like behavioral responses, physiological responses like stress, and most importantly, it drives where we're willing to go in an environment. It drives the spatio-temporal usage of an environment that an herbivore is willing to use. Now, we know that this works in Yellowstone, but we really limited in the amount of work that's been done in marine systems. So that's what we try to do. So why does this matter for this system? Well, right now, the hypothesis is herbivory, remember? But really, it's herbivory underneath this landscape of fear, this notion that herbivores are perceiving risk within their environment, and they're making choices on where to eat and how to eat based on that perceived risk of fear. And this is what this looks like in the halo. We have the structural complexity of the coral reef. We have small herbivores like our maninis here that are utilizing that as protection. They feel safe here. But because there's so many manini in that, there might not be enough food for them on the reef structure anymore. So they have to venture out in order to get their daily needs, their requirements for food. But as they do so, risk is constantly increasing away from that structure. And so if I go back here, basically the hypothesis is that these bands around the reef is essentially a proxy for how much fear is being perceived by the herbivores that use that reef, and that distance is relative to how many predators are within that system. So how do we test this? This is really difficult, and working in the ocean is always really difficult. Basically what I've done is these are gigantic cages. These fish are not to scale. These are basically massive cages that are floating in the ocean out at HIMB, where I run experiments where right here, there's a big cage that is only available to the menini or to our herbivores. That's their protective structure. I then place algae at fixed distances away from that structure, and then I put a bunch of different predators inside and measure how far away are they willing to go. Essentially, I torture small menini for a living. So let's break down what has to be done to accomplish research like this. We chose our predators, our milus, our carrying mountain pygits, because they're culturally important here in Hawaii. They're commonly fished. We know a lot about them. And they're also just voracious predators. They are literally little terrorists. Herbivores, we chose our menini. Again, incredibly culturally important, hugely abundant around Hawaii. Anybody that's been snorkeling, this is probably the second most common fish that you see. They're also super cute, so we like using them despite the fact that I torture them. But the design in general is this. I have all these systems set up, and in some of them I put 3 milus, in some of them I put 1, in some of them I put 2, and in some of them the menini are free of any predation threat. I add in 3 menini per system, and then I place, this is the central refuge that I mentioned, and then I place algae at fixed distances away from that refuge, and I measure how much of this algae gets consumed at all of these distances over time based on that risk perception. Now, that sounds simple enough, but in order to do this, I have to catch these fish. Science is never that simple. It's actually really difficult. And so most of my days look like this, where I'm fishing for amilus. I shouldn't complain, I love fishing, but I'm much better at catching a lot of other species than I am at amilus. I think I average probably 30 to 40 toau for every amilu I catch. So it's tedious and it's time consuming and it's not that much fun. But when I do catch an amilu, this is what it looks like. It's still a lot of work. It goes immediately into a bucket. I have to run to a car. I have to drive these fish all the way around the island into my experiment. I need to run them all the way down, measure them, get them allocated, and then throw them into whichever system they're going into. Again, time-lapse changes perspective. I just put like 7 minutes into 20 seconds. The menini are a little bit more fun to catch. We do nightlight fishing, so I'll go out on the reef in the middle of the night with a really bright flashlight. You smoke them right in the eyes, and they basically just go limp. And you scoop them up, super easy. I like to think of it as like abducting them, and then all of a sudden they wake up in a system where there's a bunch of really terrible predators trying to get them. So not the most fun for the menini, but it's really fun to catch them. So finally our amilu are now instilling fear in the menini instead of me thinking I'm not going to catch them. So I just want to show you a really cool video. You're going to see me throwing squid, which is how I feed the amilu, but you'll see them actually trap the squid in the air, and they'll be at where the squid lands. They're incredibly intelligent fish. They're really beautiful. They're really fun to work with, and they're really good at terrorizing menini, which is exactly what we want. So now we've set the stage, we've caught all of our fish, let's talk about what we expect to see in this experiment. In our control, where we have no amilus, these fish are free to do whatever they want, our expectation is that almost instantaneously they consume all of the algae. Why would they not? It's a free lunch, let's do it. In our one predator system, we actually expect probably the same thing. It's not too much risk. We just think it'll happen at a much slower pace. They're going to have some vigilance. They're not going to be going too crazy, but they probably will eat everything. In our two predator system, this is where we expect things to start getting a little interesting. We expect that they'll still eat quite a bit, but they're going to produce a nice large halo within the system, and they're probably going to avoid these farthest points from protection. In our three predator system, we expect the most dramatic shift. We expect that they're probably only going to eat directly where they feel the safest because this is a bad situation for a menini. So what does this look like? Basically what I'm showing you here is all of these systems. This is a fishless control, so this has no fish in it. I use this to determine the structural soundness of my algae. This is my control with no predators, one predator, two predator, three predator. The rings represent those distances of algae, the farthest being the farthest, obviously, and this around here. This allows us to kind of visualize the formation of halos. So after our first time step, boom. exactly as we expect in our control. They eat everything pretty much as they want, but you can still see that they're still not wanting to go super far from protection. Instantly, we have halos at the first distance in our 1 predator and 2 predator system. Awesome. Nothing happening in our 3 predator or our fishless control. Again, awesome. As we keep going, we start to see new patterns emerge. And I'm not going to talk about this quite yet, but I'll get to it. This is unintuitive. Why would we have herbivory happening at the farthest point? We see it in both the 1 and 2 predator system. Super funky, but I'll get into it. I'm going to kind of rip through these relatively quickly now. But as we see these patterns develop, it is exactly what we started to expect. We have a big halo formed here. We have this weird one on the outside. Again, a broader halo here. Little one on the outside. And this is what's so exciting. This is the major takeaway from this experiment, is in that massive predator system, we essentially starved them out for 3 days. And finally, they had to make a decision. It's either die or go get food. And they created a perfect halo only close to structure, exactly what we think is happening in halos. Now, before I move on too quickly, I'll show you the actual numbers. This pattern seems weird, but there is an explanation for it. If you can imagine back, I didn't put it in the slides, that would have been useful, but there is a boundary here. There's PVC and mesh netting on the outside. What's happening here is they're actually utilizing what we call a boundary effect. They're using the mesh netting as a secondary refuge. They feel safe around the netting, and it turns out that these middle grounds, where they're equidistant from the central refuge and this refuge of the netting, is the most dangerous place for them to be. So they're actually avoiding this middle ground because they have that secondary refuge. Kind of cool, kind of screwed up my data, but it's explainable and interesting.
Yeah.
So what were the major takeaways of this particular experiment is high predator density dramatically impacting that grazing behavior. Data resembles a fishless system under that maximum predation risk until you push them to a point of starvation. Halo formation is inconspicuous, but it is occurring as predicted in those 1 and 2 predator systems, despite this funky edge effect that we saw. But more importantly, for the first time, we have isolated one of these mechanisms in the broad scheme of coral reef halos, and we've shown that the landscape of fear on patch reefs can be the sole mechanism for halo formation. When everything else is controlled and you just have predators and herbivores, that species interaction and that perceived risk of fear or risk of predation can drive the patterns that we see from satellite imagery. That's really cool. Now, this isn't the only work that we're doing. I'm not going to talk too much about these because they're kind of TBD and part of my dissertation that I have not yet started. But the next project that I'm working on is looking at landscapes of fear inside and outside of Hawaiian protected areas. So we're actually using Hanauma Bay, Alapapa Reef Track out in Waikai, a site called Malawaka in Maui, as well as the Hula Ope MLCD out in Lanai. And what we're going to be doing is actually the same thing that I do in my mesocosms, but out on the actual reef. So we'll be placing algae at fixed distances away from the reef structure, inside and outside of protected areas. And the concept is, if it's protected, as anybody that's been to Hanauma can say, you have much more herbivores, you have much bigger herbivores, and you have relatively intact predator species. And so we should see very distinct patterns of how these herbivores are perceiving their environment and how far away from the reef they're willing to go. This is really cool because it's going to give us insights on the current management strategies that we have here in Hawaii, and it will also inform management strategies that are coming about from things like DAR's 30x30 initiative. So this is a project we're really, really excited about, and it's going to continue to build our understanding of how these patterns form and what they mean for us in terms of our conservation strategies moving forward. Secondarily to that, one that gets me the most excited is looking at landscapes of fear across ecosystems. How do landscapes of fear present inside marine systems or inside of more terrestrial-oriented things? And the inspiration for this was actually looking at a system called cockjays in the African Serengeti, where these rocky outcroppings are actually used by big apex predators like lions as resting areas. And things like gazelles or wildebeest actually avoid a central refuge, the opposite pattern that we see on coral reefs, where predators are more external. However, if you scale back in that ecosystem and you look at things like rodents, the rodents, which aren't on the menu for the lion, do use that central refuge, and they avoid the external threats from things like coyotes or birds of prey. So depending on where you are in the food chain, the directionality of perceived risk might change. And this is something that nobody's explored, and something I'm really excited about that I'm hoping to get to soon. Now, I just want to briefly talk about the other work that's going on in the mating labs. So obviously, Elizabeth is our driving force. She's done so much work to continue uncovering things about the reefs, and all of us together in the lab, really the ultimate goal is to use these for conservation, and all of us are taking a stab at this from different perspectives. She's done work, like I've told you already, about kind of integrating experiments to really show us where different things within different kind of levels of the food chain, where do they exist within this space around the coral halo, whether it's herbivores, bioturbators, predators. She's really opened the door for us to explore this sort of thing. She's also done a ton of work using fishing as a proxy. How does human interactions like overfishing influence predator densities? How do predator densities influence that prey behavior? And how does the behavioral shifts in prey impact the distribution of food in aquatic ecosystems? And also, a huge leader in terms of using remote sensing. Although my background came from cool webcams underwater, our lab does a ton of work using satellite imagery to monitor these patterns over long periods of time. And you can kind of see these changes occurring in these halos just in simple yearly transects. So we can see shrinkages, we can see expansions, and those might be related to seasonal effects, things like nutrient output, things like how high the sun is in the sky during a particular time of the year, or it could reflect changes that are happening in the assemblage of the reef. There might be more predators, more fishing at one point in time. But we won't know until we tease apart all of these different mechanisms. We also have Dr. Simone Franceschini, who's an AI specialist. He has developed really cool algorithms that basically just absorb satellite images and actually identify and measure the halos for us. This is a huge game changer. You have no idea how difficult it is to just manually draw circles on halos all the time. So if a machine can do it, that's awesome. Dr. Amelia Meyer is taking a huge database of shark populations from around the world and looking at where sharks are located and what the density of those predators are relates to the size of halos in different ecosystems. Dr. Emily Lester has done a ton of work similar to my own, but using like artificial sharks, so fake sharks that she'll put in like a pulley system underwater and like go scare small fish and determine how they change, where they're going. And she really has kind of led the charge on not only thinking about a plane. When we think about coral halos, it's all about what's happening on the bed, what's happening to the algae. But there's also a three-dimensional aspect to the ocean. How are they changing their willingness to go higher or lower in the water column as well? Is something that she's been a leader in kind of uncovering. And I also just want to point out, I love the hemisphere of fear. Great term. Aviv Swan, who is our lab manager, did all the dirty work before we had algorithms doing this for us, and basically created a global data set that was just published last year looking at halos across the planet. And what's amazing about them is they are everywhere. This is a ubiquitous pattern. We see it all over the world. That makes it even more interesting as a conservation tool because it's not something that's just limited to this, that, or wherever. And finally, we have Annie Niscol, the fellow PhD student in the lab with me. She's actually kind of doing a redux of what we saw before in 1965 with Jack Randall. We have a bunch of cinder blocks out in Kaneohe Bay in these seagrass beds, trying to determine and kind of, again, tease apart what's happening in terms of nutrient inputs, in terms of temperature, and how does that influence the processes that underlie the halo formations. So that's the big, broad, ongoing projects happening in our lab. They're all taking different directions to answer the same question, and that question is, what can fear do for conservation? And so the final thoughts that I have for you that I want to leave you with is we still have so much to learn about the processes and mechanisms that drive the formation of these incredible patterns. It's essential that we isolate those mechanisms and understand each of their respective roles in halo development and maintenance. That's essentially what we're doing in our lab. We can cheaply and effectively monitor these patterns from satellite imagery, making them intriguing candidates for conservation. And halos and similar vegetation patterns are fingerprints around the world that might enable us to make better management decisions, as well as provide feedback on those that we've already made. But that, I would just like to acknowledge everybody on my own committee, everybody in the lab, HIMD Facilities, who literally makes our world go round and allows us to conduct the research we do. University of Hawaii Sea Grant, who's funded this work to date. And finally, friends of Waikiki Aquarium and Waikiki Aquarium themselves, as well as St. Andrew's School, for putting this on and allowing me to do this. I feel very honored. I hope that you learned something. I hope I didn't go too fast or throw too much at you. And yeah, at that, thank you, and would love to hear any questions and chat more about those.
Question, if you like?
I also can't really see, so it's just yellow out.
So you didn't have any pictures of halos in Hawaii, but you said it's everywhere, so we've got halos here?
Yeah, so we do. Okay, so Hawaii's not the best place for halos, and there's a couple reasons why. First, it's a relatively young system, and we don't necessarily have, well, let me take a step back. The major reason we don't have good imagery of halos in Hawaii is because Hawaii is relatively deep. We don't tend to have super shallow areas. The best shallow areas that we have are Kaneohe Bay, and a little bit in some of the reef tracts like Lanikai or even Waikiki. In order to see them from satellite imagery, it has to be shallow. If it goes deeper, the satellite's not seeing the surface. You're just getting reflectance of the ocean, so you're getting a blue image. However, we do see halos. We know that there are halos in about 60 feet of water in Maui. And actually, just recently, ironically enough, we saw a really cool video that was taken by a spear fisherman in Ni'iau. He was in about 200 feet of water, and as he got to the bottom, there were thousands of very small halos in the sediment down there that we think are probably being driven by urchins. So we do have them here. They're just too deep for us to see on satellite images.
I was going to follow up, and my thought was, well, why don't you use your cool underwater photography to get down there and see if you can actually, in real life, what you're trying to get.
Yeah, for sure. I think one of the major things that we still need to do is the classic halos that we see, the best ones in the world are in the Red Sea, like up north in the Red Sea. They're so remote that nobody's actually gone and the one thing that I wish that I could do is just, I want to know what algae is there. We know that they're perfect halos. We know that they persist over time. We've just never put humans in the water to actually see them, take images. So that's something we're very keen to do. But at the end of the day, you do have some minor requirements that you need for a halo. You need to have a coral-algal interface, right? If there's no algae, there's no halo at the end of the day. So you do need that inherent property. And then you tend to see them more with patch reefs. And that's one of the other things that we don't really have here in Hawaii. You don't tend to see patch reefs that often. We have a lot of spur and groove and fringing reefs. And even when you look at Kaneohe, you have about 100 feet of water, and then you have these massive reef structures coming out of them, which could kind of act as a patch reef, but you don't have that shallow nature directly around it to see that kind of algal interface. So yeah, Hawaii, unfortunately, is probably not the best place to look for them. But luckily, we can manipulate systems to see it happen artificially, if that makes sense. But I think you raise a really good point. It's not a conservation tool for everywhere, right? You have to have a history of these being there in order for it to be useful. But in doing the research, I think that you also you provide cool new methodologies to explore the properties that exist. So for instance, this project that we're starting inside and outside of managed areas here in Hawaii, we can outplant algae, and the way that that data comes back still tells us a great deal, even if that algae isn't necessarily naturally occurring and creating halos in and of itself. Easy crowd.
When I look at that, I think about, you see kids cross through grass and eventually they cross the snuff in the same pattern and then the path emerges.
Sure.
And so is there anybody that's just looking at just the presence and I guess turbidity of the swimming fish around that area in addition to the grazing? So we just keep the path essentially.
Yeah, so we do see, so all of this work that's being done on satellite, and I'm not a satellite expert, I'm definitely a fish behavior guy, so my answer is going to be meh. I do know that like path creation in terrestrial systems is of huge interest in terms of what we're able to do with satellite imagery now. I think there's even somebody here at the University of Hawaii that's actually trying to do exactly that with some of the local hogs, so looking at their paths in places like on the Big Island. In terms of doing that underwater, I think it's really a question of like bioturbation. So I don't necessarily know if you would see pathways. I think there are some circumstances. Let's see if we can pull, I don't know how far back I have to go. So if we look at some of these images, I think what you're trying to describe would be something like, so in a couple of these, like right in these right here, there might be like kind of a pathway where they're just the perfect distance where that sand doesn't quite match up, but you might actually have a pathway of like immigration that you could measure and see as they expand or contract where the sand starts to get close enough to where you might have something like that. But I think the better way to kind of answer that question would be yeah, like live cameras underwater looking at the amount of things like stingrays, things that bury themselves or stir up the sand regularly and see how regular and how intense that sort of thing is. But as far as I know, nobody's tried to do that yet, but it's a really cool thought.
Are you saying within that ring, so you have like the manini and they stay within that ring, so is it the same family of fish? Are they just breeding with themselves in there, or are they?
In my systems?
Well, in any of these, are we looking at the fish too, that they're related, that they are the same fish, that they're not like migrating to the other side of the reef? It's really,
Yeah, totally.
Is there a way to, are we testing like, I don't know, is there a way to find out if they're the same?
Yeah, it's a really good question. I guess the exact same individuals, it's really hard underwater. There are ways that we could do that, but you still sort of would need to like enclose a patch reef, for instance.
Like, I don't know if there's any fish DNA that you can say there, that's the.
Yeah, sure. I think
fuzzy
actually,
on this fish.
so this is something that I would love to do, but it's probably like not feasible. Would be to set up, like you have a patch reef and you can kind of close it off, but at scale. And what you can do is you can use something called an elastomer, which is basically like giving a fish a tattoo. So you can give them basically color-coded tattoos that allow you to identify individuals. And then you can have a long-term study looking at exactly what the individual nature is within that system. Perhaps you do have like within species variability where certain individuals are more willing to take risks or certain individuals are more skittish, which certainly exists. In the aquarium industry, right, they're just like cats or dogs. You have some fish that are really personable, really interesting, and some of them are super skittish. You put them in an aquarium and you never see them again because they're just hiding all the time.
Well, if they're genetically all kind of just staying the same within a certain area, I'm wondering if like a manini on Big Island is different from, do they start evolving differently from, because they're not.
Yeah.
You know what I mean?
So I'm not a geneticist, but what I do know is you do have like very distinct subpopulations in the Big Island, for instance, in the Maui Nui complex, on Oahu, on Kauai, and then you also have very distinct populations in the Northwesterns. And that's largely driven by the fact that we have very strong currents between the islands, that when you do have spawning events, you have these kind of natural barriers that are disallowing too much intermixing. But obviously, when we think about Hawaii as this amazing natural laboratory, because geologically speaking, it's incredibly young, and so the species that are here had to come from somewhere. And so the current hypothesis is that you have Johnston Atoll and the Northern Line Islands essentially feeding different species of fish or coral up through that chain, they end up in kind of the middle of the northwestern Hawaiian Islands, and then you can slowly see them start to dissipate. And this is the reason why we have so much endemic species here in Hawaii, is because over those handful of millions of years, they have evolved to the point where they are not only genetically distinct from their partners throughout the rest of the Pacific that may look similar, but they also in some circumstances are just completely different species. So that's certainly something that's happening. I think to maybe go a little bit farther into that from a behavioral perspective, when you look at like an individual family, for instance, like the surgeonfish, their behaviors are largely going to be very similar. I think there's going to be some differentiation happening based on body size. So for instance, a really massive surgeonfish may not be that scared of a relatively small amilu simply because the amilu's gape size is just not big enough for it to be that threatening to that particular fish. Whereas the same species, perhaps even the same genotype, that's quite small is probably going to behave very differently simply because of that size difference. So there's this kind of like unlimited number of variability even within the same species that's going to drive how they're behaving. Some of those are life history traits. Some of them are probably where they are in the world. I think one of the most interesting questions that we could ask that have been done in terrestrial systems for landscapes of fear have been done on rodents. So there's a guy named Sony Bleicher who looks at the evolutionary history of how fear is perceived. And basically what he's done is he takes rodents that have an evolutionary history of anti-predator defenses towards things like snakes, and then another rodent that has a history of anti-predator defenses towards an aerial attack from a thing like a bird of prey. He'll put both of those rodent species into enclosures similar to me, and then he'll put snakes in one, he'll put aerial or birds of prey in another, and then he'll intermix everything in other systems and look at how the evolutionary history of having this very distinct perception of a bird of prey, how well do you do when the risk is something different like a snake and vice versa. So that would be really cool to do in a system like this where you could take like an invasive species, for instance, like the lionfish in the Atlantic, and look at how anti-predator defense or the behavioral shift because of perceived risk. Do you even see the lionfish as a risk because it's something novel to you? It's not something that you're used to seeing in your environment, so you might not do anything and you might just get eaten. So lots of cool ways to answer those questions. Unfortunately, I'm not the one doing it right now, but it sounds like a lot of fun.
Well, now that you identified the halo and how they're behaving on the halo, it does open up a whole lot of other questions about what are those fish? Along those, I mean, there's like a million questions I have.
Yeah, for sure. I mean, it's definitely, the herbivores I think we definitely know are, the surgeonfish I think are probably the major drivers. I'm sure that the parrotfish are also playing a pretty significant role because they do consume more and more frequently. I think the more interesting question for me right now is what predators are actually like the most scary. So like some of the preliminary information that we've seen when we're looking at sharks, for instance, we haven't necessarily found like a huge pattern with sharks. And I think that as we move more towards the mesopredators, things like carangids and jacks, that are pretty voracious predators and maybe spend a little bit more time around the reef, I think those patterns might start to come up a little bit more. But yeah, I couldn't agree more. Actually, teasing apart the exact species that are the most important ones, that's certainly the next step.
Well, it's the same phenomenon you talked about with the lions and the rats. Like
Yeah.
they're hanging out in the same zone because they're not really worried about
For
each
sure.
other.
Who's on the menu? Who's scared of who the most? What's the intensity? How do we find those answers? And it's just really hard and time consuming to do that. But
So you didn't actually give examples of how you think this could influence marine management. Like just that it's good information to have to use, but how do you imagine somebody then making decisions off of what you're finding?
yeah, sure. So I think that the biggest one is the work that's been done using fisheries. So the one example that I very, very briefly skimmed over that had a lot of information on the slide, essentially what Elizabeth was able to do there was use the Line Islands as an interesting conservation example because we have a gradient of fishing pressure. So Palmyra Atoll, which is an incredibly amazing place that has zero fishing, is completely regulated and basically run by the Nature Conservancy. has huge predator populations that quite frankly just don't exist in many places on Earth anymore. And then just below that you have Kiribati and then Korean atolls, which have actually relatively high human density effects. Lots of people living on those atolls, and they almost exclusively are making by fishing. So you have these very similar ecosystems. You don't have huge discrepancies between the types of species that are there. But again, you have this natural laboratory where you have overfishing that's certainly happening. You've influenced the amount of predators within that system. And then you have an intact predator system in Palmyra. And what we saw was really interesting because we definitely see different behavioral changes in the herbivores. Their home ranges, how much space or excursions they're willing to do, are significantly higher in these fished areas. And the only attribute that we can significantly attribute to that is the lack of predators. The interesting thing with that is, what we also found in that study is that on bigger reefs, because a bigger reef means you have more herbivores and higher abundance or higher density, that seems to be also a much larger factor in driving how far away that halo is created. But basically that study allowed us to show that in an overfished ecosystem, we can see fundamental shifts in how the behavior is playing out with the herbivores. And so what we're trying to do here in Hawaii now is, because we have this developed plan in 30 by 30 with DAR, is can we go out, place algae in a similar way that what was done in Palmyra and Kiribati, and see what the effectiveness of protected areas are currently in Hawaii, which helps us make a decision as to whether we should design systems as they have already been designed, or is it going to provide us any information that might allow us to think a little bit more about how do we protect herbivores in particular, which has been a topic of discussion in terms of what DAR's interests have been. But I think the coolest thing is, how does protecting predators actually trickle down within these systems? If we're trying to influence herbivores here in Hawaii from a conservation perspective, protecting herbivores might not actually be the best methodology. It might actually be protecting the predators because of these trickling down effects and because of the behavioral regulations that we see in those systems. So that's kind of the ultimate goal. That's certainly like a 30,000-foot view and probably more of a 10-year plan. Yeah, again, we have to tease apart all of the mechanisms to really be able to say anything for certain. But yeah, all that interconnection makes us really hopeful that they're good conservation tools. And I think that everything to date is pointing towards that. But obviously, we could always be wrong. That's just the name of the game in science. Be hopeful, try and prove it. And if it goes otherwise, then hopefully it's asking, opening new doors and new questions that can also be useful. It's a great question, though. Thank you. Thank you, guys.
Thank you.
For those of you who may not know me, my name is Beth Churchill. I'm the Interim Executive Director of the Friends of the Waikiki Aquarium, and just want to send out a big thank you to everyone for attending tonight's Tim Gard Distinguished Lecture Series. And this series is dedicated to honoring our esteemed former board member and cherished local waterman, the late Tim Gard. And a special thanks to Zach for investing your time and your energy in creating and delivering such an incredible presentation. Really well done. Thank you. A special thank you to St. Andrew's School for allowing us to use Tenny Theater and their ongoing support of the Friends of the Waikiki Aquarium and the aquarium itself. And I'd like to send out a quick reminder that this weekend is the 16th annual Mauga Environmental Expo at the aquarium. So Saturday, April 15th from 9 a.m. to 2 p.m. It is the only free day at the Waikiki Aquarium each year, which is exciting. It's a free, family-friendly event, and it promotes the importance of keeping Hawaii clean and pollution-free from the mountains to the sea. So we'd love to see you there. And thank you to all of our members who have attended tonight. We really appreciate your support. And if you are not currently a member of FOA, we would love for you to become one. There are a lot of great benefits being a member. You stay informed about upcoming events like Distinguished Lecture Series. You receive exclusive invitations to our members-only events. You enjoy discounted admissions, and you gain access to many other events. And at certain levels, you can actually use the aquarium for evening events. So a lot of really, really wonderful benefits. And if you're interested, please go to fowaquarium.org and you can check out our membership section. So thank you all for attending. I thought this was a really amazing presentation. Zach, well done. Thank you. And we hope to see you at a future Waikiki Aquarium event coming up, or our Keikani o Kekai series this summer. So thank you all for attending, and we hope to see you soon. Aloha.